Hello there, and welcome to Cosmic Sleepy Science. I'm so glad you've decided to join us tonight. Before we begin, a quiet question. Where are you in this moment? A bedroom where shadows rest softly against the walls. A familiar space where the day finally releases its hold. Wherever you find yourself, you are exactly where you belong. Let your body settle into stillness. There is nowhere else to be, nothing left to do. Tonight, we drift through the invisible world of atoms. We'll move slowly through the building blocks of everything you see and touch. Rest within the forces that hold matter together and float peacefully across the bonds that connect all things in existence. There is no need to stay awake. If sleep finds you along the way, let it come. These words will continue without you. There is no test, no memory required. Only rest. If these peaceful journeys bring you comfort, a gentle like, comment, or subscribe helps this quiet space continue. And if you're already here with us, thank you. Your presence means more than words can hold. One deep breath, and we begin. Everything around you is made of atoms. The pillow beneath your head, the air moving quietly through your lungs, the screen displaying these words, the body reading them. All of it, without exception, built from the same fundamental pieces. Atoms are small beyond ordinary comprehension. A single human hair, thin as it seems, contains millions of atoms across its width. A grain of sand holds more atoms than there are stars visible in the night sky. Yet despite their size, atoms are not the smallest things that exist. Each atom contains even smaller components. A dense center called the nucleus, and surrounding that nucleus, a cloud of particles called electrons that move in patterns we can only describe, never truly see. The nucleus itself holds two types of particles: protons, which carry a positive electrical charge, and neutrons, which carry no charge at all. Together, these particles account for nearly all of an atom's mass, packed into a space so small it defies imagination. The electrons exist outside this nucleus, occupying regions of space called orbitals. They carry a negative electrical charge, perfectly balancing the positive charge of the protons in a stable atom. This balance creates neutrality. An atom with equal protons and electrons has no overall charge. But electrons do not orbit the nucleus the way planets orbit a star. That image, though common, misleads. Electrons exist in clouds of probability, regions where they are likely to be found rather than specific paths they follow. Quantum mechanics governs their behavior, and quantum mechanics operates by different rules than the visible world. The number of protons in an atom's nucleus defines what element that atom represents. One proton makes hydrogen, the lightest element. 6 protons make carbon, the foundation of organic life. 79 protons make gold, precious and dense. The periodic table organizes elements by this simple count, from 1 proton to over 100. Neutrons add mass, but do not change an element's identity. Carbon with 6 neutrons is carbon. Carbon with 8 neutrons is still carbon, just a different isotope. The chemical behavior remains the same because chemistry depends on electrons, and electrons depend on protons, not neutrons. Most of an atom is empty space. If you could enlarge an atom to the size of a sports stadium, the nucleus would be a marble at the center, and the electrons would be tiny specks moving somewhere in the outer stands. The rest, vast and hollow, contains only fields of force. Yet this emptiness does not mean atoms are fragile. The forces holding an atom together rank among the strongest in nature. The electromagnetic force binds electrons to the nucleus. The strong nuclear force holds protons and neutrons together despite their tendency to repel. These forces operate at scales where human intuition fails, but their effects shape everything. Atoms existed long before Earth formed. The hydrogen in your body was created in the first moments after the Big Bang, when the universe cooled enough for protons and electrons to combine. The carbon in your cells was forged in the core of ancient stars, where intense heat and pressure fused lighter elements into heavier ones. When those stars exploded, they scattered these atoms across space. Over billions of years, clouds of these atoms collapsed under gravity, forming new stars and planets. Some atoms gathered into rocks, others into oceans, still others into the molecules that would eventually become life. Every atom in your body has traveled an unimaginable distance through time and space to arrive at this moment. Atoms do not age. They do not wear out. A carbon atom today is identical to a carbon atom from 4 billion years ago. They can be rearranged, combined, separated, but the atoms themselves remain unchanged. You are made of ancient matter, atoms that have been part of countless forms before becoming part of you. This continuity connects all things. The oxygen you breathe was once part of a tree, and before that, part of the atmosphere, and before that, released by ancient algae. The calcium in your bones was once part of a shell, and before that, dissolved in the ocean, and before that, formed in a dying star. Nothing is truly separate. Everything exchanges atoms constantly. Atoms bond together to form molecules. 2 hydrogen atoms bond with 1 oxygen atom to create water. 6 carbon atoms arrange in a ring with other atoms attached to create glucose. Millions of atoms combine in precise arrangements to create proteins, the machinery of living cells. The complexity of life emerges from simple atoms following simple rules. But what makes atoms bond? Why do they come together in specific patterns instead of remaining separate? The answer lies in energy. Atoms bond because doing so releases energy, moving them into a more stable state. Nature favors stability. Systems naturally move toward lower energy configurations. Bonding achieves this. Electrons drive this process. Atoms bond by sharing electrons, transferring electrons, or allowing electrons to interact in ways that lower the overall energy of the system. The outer electrons, called valence electrons, determine an atom's chemical behavior. These are the electrons that interact when atoms approach each other. Some atoms hold their valence electrons loosely. Sodium, for example, has 1 electron in its outermost shell, far from the nucleus and weakly bound. Other atoms have nearly complete outer shells and desperately attract additional electrons. Chlorine needs just 1 more electron to complete its outer shell. When sodium meets chlorine, the sodium gives up its loose electron, the chlorine accepts it, and both atoms become more stable. This stability comes from a simple principle. Atoms are most stable when their outermost electron shell is full. Helium, neon, argon, and other noble gases already have full outer shells. They rarely bond with other atoms because they are already stable. They exist contentedly alone. But most atoms do not have this natural stability. They must find it through bonding. Hydrogen has 1 electron but wants 2. Oxygen has 6 outer electrons, but wants 8. Carbon has 4 outer electrons, but wants 8. These desires, these tendencies towards stability, create the entire landscape of chemistry. When atoms bond, they lower their energy. Energy is released, often as heat or light. Breaking bonds requires adding energy back into the system. This is why burning releases heat. The chemical bonds in wood or fuel break and reform into new, more stable arrangements, and the difference in energy escapes as warmth. The strength of a bond depends on how much energy is released when it forms, or equivalently, how much energy is required to break it. Strong bonds hold atoms tightly together. Weak bonds allow atoms to separate easily. The bonds between atoms in a diamond are extremely strong, making diamond the hardest natural material. The bonds between water molecules are much weaker, allowing water to flow. Atoms bond in different ways depending on their nature. Metals bond by allowing electrons to move freely between atoms, creating a sea of shared electrons. This electron mobility gives metals their characteristic properties: conductivity, malleability, shine. Nonmetals bond by sharing or transferring specific electrons, creating distinct molecules with defined structures. The periodic table organizes atoms by properties, revealing patterns. Elements in the same column have similar bonding behavior because they have the same number of valence electrons. The leftmost column, the alkali metals, all have 1 valence electron and bond readily. The rightmost column, the noble gases, all have full outer shells and rarely bond. Between these extremes lies incredible variety. Carbon, with 4 valence electrons, can bond in countless ways, creating millions of different molecules. Silicon, directly below carbon on the periodic table, shares this versatility. Nitrogen, oxygen, sulfur, and phosphorus each bond in characteristic patterns, creating the molecules essential to life. Understanding atoms means understanding patterns, not memorizing facts, but recognizing tendencies. Atoms with few valence electrons tend to lose them. Atoms with nearly full outer shells tend to gain electrons. Atoms with half-filled shells tend to share electrons. These tendencies, rooted in the pursuit of stability, generate all chemical diversity. Yet despite this diversity, certain rules remain constant. Conservation of mass means atoms are neither created nor destroyed in chemical reactions, only rearranged. Conservation of charge means the total electrical charge before and after a reaction stays the same. These conservation laws constrain what reactions are possible. Atoms bond because the universe favors lower energy states. A boulder on a hilltop will roll downward because the valley represents lower gravitational potential energy. A hot object will cool because thermal equilibrium represents lower energy imbalance. An atom with an incomplete outer shell will bond because a filled shell represents lower energy. The principle is universal. Time does not affect atoms directly. An isolated hydrogen atom today is identical to one from the early universe. Atoms do not decay unless they are radioactive isotopes, and even then, only the nucleus changes while the electron configuration remains governed by the same rules. Chemistry is timeless in this sense. The same rules that applied billions of years ago apply now. Pressure and temperature, however, dramatically affect how atoms bond. High pressure forces atoms closer together, sometimes creating bonds that would not form otherwise. Diamond forms under extreme pressure deep underground, where carbon atoms are forced into a rigid lattice. At normal pressure, carbon prefers graphite, a softer arrangement. Temperature adds energy to atoms, making them vibrate and move faster. High temperatures can break bonds that are stable at low temperatures. This is why ice melts and water boils. The thermal energy overcomes the attractive forces holding molecules together. Cooling reverses the process, allowing bonds to form and stabilize. In the coldest regions of space, atoms move so slowly that even weak attractions can hold molecules together. Complex molecules form in interstellar clouds where temperatures approach absolute zero. These molecules drift for millions of years, sometimes landing on planets, sometimes becoming part of new solar systems. On Earth, moderate temperatures allow a rich diversity of bonding. Liquid water exists because temperatures are high enough to prevent freezing, but low enough to prevent boiling. This narrow range makes life possible. Too cold, and chemical reactions slow to a stop. Too hot, and molecules break apart faster than they can form. Atoms bond not just in pairs, but in vast networks. A single crystal of salt contains trillions of sodium and chloride ions arranged in a repeating pattern. A single diamond contains countless carbon atoms bonded in a three-dimensional grid. A protein molecule contains thousands of atoms precisely arranged to perform a specific function. Scale varies, but the principles remain the same. Living organisms are, at their most fundamental level, carefully organized collections of bonded atoms. Your DNA is a long chain of atoms arranged in a sequence that encodes information. Your muscles are proteins, molecules made of atoms bonded in patterns that allow contraction. Your thoughts arise from electrical signals moving through atoms in your brain. Life is chemistry in motion, yet atoms themselves are not alive. They do not think or intend. They follow physical laws with perfect consistency. The complexity of life emerges from simple atoms interacting according to simple rules, repeated across unimaginable scales. Complexity does not require complexity at its foundation. Simple rules, applied universally, create everything. This realization brings a certain peace. You are made of atoms, and atoms follow knowable rules. There is no mystery about what you are made of, only wonder at how these simple pieces arrange themselves into consciousness. The elements in your body are the same elements in stars, in planets, in the vast emptiness between galaxies. You are not separate from the universe. You are the universe, temporarily organized into a form that can contemplate itself. Atoms bond because it is energetically favorable. But from this simple tendency emerges all matter, all structure, all complexity. The universe is not random. It is deeply organized, following principles that can be understood. And those principles begin here, with atoms seeking stability in each other's presence. To understand why atoms bond, we must first understand electron shells. Electrons do not swarm randomly around the nucleus. They occupy specific regions of space, organized into layers called shells or energy levels. Each shell can hold a limited number of electrons, and this limit shapes all of chemistry. The first shell, closest to the nucleus, can hold a maximum of 2 electrons. Hydrogen has 1 electron in this shell. Helium has 2, filling the first shell completely. With a filled shell, helium is stable and rarely interacts with other atoms. This is why helium is a noble gas, inert and unreactive. The second shell can hold up to 8 electrons. Lithium has 3 electrons total, 2 in the first shell and 1 in the second. This single electron in an outer shell makes lithium reactive. It easily loses that electron to achieve the stability of a filled inner shell. Beryllium has 4 electrons, 2 in each of the first 2 shells. Boron has 5. Carbon has 6. Nitrogen has 7. Oxygen has 8. Fluorine has 9. Neon has 10. Neon, with a filled second shell, is another noble gas. Like helium, it rarely bonds with other atoms because it has already achieved maximum stability. The pattern becomes clear. Atoms with filled outer shells are stable and unreactive. Atoms with partially filled outer shells are reactive, seeking to fill or empty those shells through bonding. The third shell can also hold up to 8 electrons in most cases, though technically it can accommodate more in certain configurations. Sodium has 11 electrons, 2 in the first shell, 8 in the second, and 1 in the third. That single outer electron makes sodium highly reactive, similar to lithium. Magnesium has 2 outer electrons. Aluminum has 3. Silicon has 4. Phosphorus has 5. Sulfur has 6. Chlorine has 7. Argon has 8. Argon, with a filled third shell, is yet another noble gas. The pattern continues throughout the periodic table. The noble gases mark the end of each row because they represent filled outer shells. Every other element falls somewhere in the process of filling or emptying shells. The electrons in the outermost shell are called valence electrons. These electrons determine how an atom bonds. Inner electrons are held too tightly by the nucleus to participate in bonding. They remain with their atom regardless of what happens. But valence electrons exist at the boundary between the atom and the outside world. They can be shared, transferred, or influenced by nearby atoms. An atom with 1 valence electron tends to lose it. Removing that single electron leaves behind a filled shell, achieving stability. Sodium, with 1 valence electron, easily loses it to become a sodium ion with a positive charge. The loss of a negatively charged electron leaves the atom with more protons than electrons, creating a net positive charge. An atom with 7 valence electrons tends to gain 1 more. Adding a single electron completes the outer shell, achieving stability. Chlorine, with 7 valence electrons, easily gains 1 to become a chloride ion with a negative charge. The addition of a negatively charged electron gives the atom more electrons than protons, creating a net negative charge. Atoms with 2, 3, or more valence electrons typically lose those electrons if they are metals. Magnesium loses 2 electrons. Aluminum loses 3. These losses create positively charged ions called cations. The number of electrons lost equals the ion's positive charge. Atoms with 6 or 5 valence electrons typically gain electrons if they are nonmetals. Oxygen gains 2 electrons. Nitrogen gains 3. These gains create negatively charged ions called anions. The number of electrons gained equals the ion's negative charge. Atoms with 4 valence electrons, like carbon, rarely form simple ions. Losing 4 electrons requires too much energy. Gaining 4 electrons is also difficult. Instead, carbon shares electrons, forming covalent bonds where electrons are held between 2 atoms simultaneously. This sharing allows both atoms to behave as if they have filled outer shells. The desire for a filled outer shell, often called the octet rule, explains most chemical bonding. Octet means 8, and most atoms are stable with 8 valence electrons. Hydrogen and helium are exceptions, stable with 2 electrons because their first shell holds only 2. But for atoms beyond helium, 8 valence electrons represent stability. This rule is not absolute. Many molecules exist where atoms have more or fewer than 8 valence electrons. But the octet rule works as a general principle, explaining the bonding behavior of the most common elements. It provides a framework for predicting how atoms will interact. Valence electrons can be represented using Lewis dot structures, a notation system that shows each valence electron as a dot around an element symbol. Carbon with 4 valence electrons appears as a C with 4 dots. Oxygen with 6 valence electrons appears as an O with 6 dots. These diagrams help visualize how atoms share or transfer electrons during bonding. When sodium meets chlorine, the single valence electron of sodium transfers to chlorine. Sodium becomes a positive ion with a filled second shell. Chlorine becomes a negative ion with a filled third shell. Both achieve stability. The opposite charges then attract each other, forming an ionic bond. The sodium and chloride ions arrange into a crystal lattice, creating table salt. This transfer of electrons characterizes ionic bonding. One atom loses electrons, another gains them, and the resulting ions attract through electromagnetic force. Ionic bonds are strong, requiring significant energy to break. This is why salt crystals are solid at room temperature, and why ionic compounds typically have high melting points. When 2 hydrogen atoms meet, neither can easily lose or gain its single electron. Instead, they share. Each hydrogen atom contributes 1 electron to a shared pair that orbits both nuclei. This shared pair creates a covalent bond. Both atoms behave as if they have 2 electrons, achieving the stability of helium. The molecule formed is hydrogen gas. Covalent bonding characterizes molecules made of nonmetals. Oxygen atoms share electrons to form oxygen gas. Nitrogen atoms share electrons to form nitrogen gas. Carbon and hydrogen share electrons to form methane. The shared electrons belong to both atoms simultaneously, satisfying the octet rule for both. Some covalent bonds involve sharing 2 pairs of electrons, creating double bonds. Oxygen typically forms double bonds, with each oxygen atom sharing 2 electrons with another. Carbon dioxide contains 2 double bonds, one between carbon and each oxygen atom. Double bonds are stronger than single bonds and hold atoms more tightly together. Triple bonds involve sharing 3 pairs of electrons. Nitrogen gas contains a triple bond, making it extremely stable and unreactive. Breaking a triple bond requires substantial energy, which is why nitrogen gas is so chemically inert despite being abundant in Earth's atmosphere. The electrons in a covalent bond are not always shared equally. Some atoms attract electrons more strongly than others. This property is called electronegativity. Fluorine is the most electronegative element, pulling electrons toward itself with great force. Francium is the least electronegative, holding electrons weakly. When 2 atoms with different electronegativities form a covalent bond, the shared electrons spend more time near the more electronegative atom. This creates a polar covalent bond, where one end of the bond is slightly negative and the other slightly positive. Water is a polar molecule because oxygen is more electronegative than hydrogen, pulling the shared electrons toward itself. Polarity has profound consequences. Polar molecules attract each other through weak interactions called dipole-dipole forces. Water molecules stick together because the slightly positive hydrogen of one molecule attracts the slightly negative oxygen of another. This attraction gives water its unique properties: high boiling point, surface tension, ability to dissolve many substances. Nonpolar molecules, where electrons are shared equally, do not have these attractions. Oils and fats are nonpolar, which is why they do not mix with water. The saying, "like dissolves like," reflects this principle. Polar substances dissolve in polar solvents. Nonpolar substances dissolve in nonpolar solvents. Chemistry is selective. Some atoms can form multiple bonds with different atoms, creating complex molecules. Carbon's 4 valence electrons allow it to bond with 4 other atoms simultaneously. This versatility makes carbon the foundation of organic chemistry. A single carbon atom can bond to 4 hydrogen atoms, forming methane. Or it can bond to other carbon atoms, forming chains, rings, and branch structures of limitless variety. Silicon, directly below carbon on the periodic table, also has 4 valence electrons and similar bonding patterns. But silicon atoms are larger, making their bonds longer and weaker. Silicon-based molecules are less stable than carbon-based ones, which is why life on Earth is carbon-based rather than silicon-based. Carbon's size and bonding strength hit an optimal balance. Sulfur, with 6 valence electrons, typically forms 2 bonds, but can form more in certain molecules. Phosphorus, with 5 valence electrons, can form 3 or 5 bonds depending on the circumstances. These variations show that bonding rules are guidelines, not strict laws. Atoms adapt to their environment in ways that maximize stability. The geometry of molecules depends on how electron pairs arrange themselves around an atom. Electron pairs repel each other because they all carry negative charge. To minimize repulsion, electron pairs arrange themselves as far apart as possible. 2 pairs form a linear arrangement. 3 pairs form a trigonal planar arrangement. 4 pairs form a tetrahedral arrangement. Methane has 4 bonding pairs around carbon, creating a tetrahedral shape. Water has 2 bonding pairs and 2 lone pairs around oxygen, creating a bend shape. Ammonia has 3 bonding pairs and 1 lone pair around nitrogen, creating a pyramidal shape. The shape of a molecule influences its properties and how it interacts with other molecules. Understanding electron shells and valence means understanding the foundation of chemistry. Every reaction, every bond, every molecule traces back to electrons seeking stable configurations. The complexity of the natural world emerges from this simple principle, repeated across countless atoms in endless combinations. Atoms do not bond randomly. They bond according to patterns determined by their electron configurations. These patterns can be predicted, understood, and manipulated. Chemistry is not magic. It is the logical consequence of electrons, protons, and neutrons interacting according to fundamental physical laws. You are made of atoms following these rules. The calcium in your bones forms ionic bonds with phosphate. The carbon in your cells forms covalent bonds with hydrogen, oxygen, and nitrogen. The iron in your blood is bound within a complex organic molecule called hemoglobin. Every substance in your body exists because electrons have arranged themselves into stable configurations. There is beauty in this order. The same rules that govern a grain of salt govern the most complex proteins. Scale changes, but principles remain. And those principles are knowable, understandable, accessible to any mind willing to contemplate them slowly and carefully. Let these ideas settle. There is no urgency, no pressure to remember every detail, only the gentle recognition that matter is organized, that patterns exist, that understanding is possible. Rest in that knowledge. Ionic bonding occurs when electrons transfer completely from one atom to another. The atom that loses electrons becomes a positively charged ion. The atom that gains electrons becomes a negatively charged ion. The opposite charges attract, binding the ions together. This type of bonding typically occurs between metals and nonmetals. Metals, found on the left side of the periodic table, have few valence electrons that they hold loosely. Nonmetals, found on the right side, have nearly full outer shells and strongly attract additional electrons. When these two types of atoms meet, electron transfer is energetically favorable. Consider sodium and chlorine again. Sodium has one valence electron. Removing it requires energy, but not an enormous amount. Chlorine has 7 valence electrons. Adding one more releases energy because the completed shell is very stable. When sodium transfers its electron to chlorine, the energy released by chlorine exceeds the energy required by sodium. The overall process releases energy, making it spontaneous. Once the transfer occurs, sodium has one more proton than electrons, giving it a +1 charge. Chlorine has one more electron than protons, giving it a 1 charge. The electromagnetic force between opposite charges pulls the ions together. This attraction is strong, much stronger than the forces between neutral atoms. Ionic compounds do not exist as individual molecules in the way covalent compounds do. Instead, ions arrange themselves into vast 3-dimensional lattices. Each sodium ion surrounds itself with chloride ions. Each chloride ion surrounds itself with sodium ions. The pattern repeats throughout the crystal, creating a structure with no distinct beginning or end. The formula sodium chloride does not mean one sodium atom bonded to one chlorine atom. It means the ratio of sodium ions to chloride ions in the crystal is 1:1. A grain of salt contains trillions of ions in this ratio, all held together by the cumulative attraction of opposite charges. The lattice structure gives ionic compounds characteristic properties. They are typically hard because the orderly arrangement resists deformation. They are brittle because shifting the lattice misaligns charges, causing repulsion and fracture. They have high melting points because breaking the lattice requires overcoming the strong attraction between many ions simultaneously. Ionic compounds dissolve in water because water molecules are polar. The slightly positive hydrogen end of a water molecule attracts negative ions. The slightly negative oxygen end attracts positive ions. These attractions pull ions away from the lattice and surround them with water molecules, a process called solvation or hydration. Once dissolved, the ions move freely through the solution. This allows ionic solutions to conduct electricity. Electricity is the flow of charged particles. In a solid ionic compound, the ions are locked in place and cannot move, so no conduction occurs. But in solution, or when melted, ions become mobile, allowing current to flow. Not all metals and nonmetals form simple 1:1 ionic compounds. Magnesium has 2 valence electrons and loses both to become magnesium 2+. Oxygen has 6 valence electrons and gains 2 to become oxygen 2-. When magnesium and oxygen combine, the ratio is 1:1, forming magnesium oxide. The charges balance. Aluminum has 3 valence electrons and loses all 3 to become aluminum 3+. Chlorine gains 1 electron to become chloride 1-. To balance charges, 1 aluminum ion must combine with 3 chloride ions, forming aluminum chloride. The formula reflects the charge balance necessary for a neutral compound. Calcium has 2 valence electrons and loses both to become calcium 2+. Nitrogen has 5 valence electrons and gains 3 to become nitride 3-. To balance charges, 3 calcium ions must combine with 2 nitride ions, forming calcium 3-nitride 2. The ratios ensure that the total positive charge equals the total negative charge. This charge balance is a fundamental requirement. Ionic compounds must be electrically neutral overall. The number and charge of cations must equal the number and charge of anions. This rule allows prediction of formulas from the charges of the ions involved. Some atoms can lose different numbers of electrons depending on circumstances, creating ions with different charges. Iron can lose 2 electrons to become iron 2+ or 3 electrons to become iron 3+. Copper can lose 1 electron to become copper 1+ or 2 to become copper 2+. These variable charges reflect the complex electron configurations of transition metals. The energy required to remove electrons from an atom is called ionization energy. It varies across the periodic table. Elements on the left have low ionization energies, losing electrons easily. Elements on the right have high ionization energies, holding electrons tightly. This variation explains why metals and nonmetals behave differently. The energy released when an atom gains an electron is called electron affinity. It also varies across the periodic table. Nonmetals typically have high electron affinities, meaning they release significant energy when gaining electrons. Metals have low electron affinities and do not gain electrons readily. Ionic bonding occurs when the combination of ionization energy and electron affinity results in a net release of energy. Sodium's low ionization energy and chlorine's high electron affinity make their combination energetically favorable. The lattice energy, the energy released when ions arrange into a crystal, further stabilizes the compound. Lattice energy depends on 2 factors: the charge of the ions and the distance between them. Higher charges create stronger attraction. Smaller ions compact more closely, increasing attraction. Magnesium oxide has higher lattice energy than sodium chloride because magnesium and oxide ions are both doubly charged and smaller than sodium and chloride. This higher lattice energy gives magnesium oxide a much higher melting point than sodium chloride. Magnesium oxide melts at over 2,800 degrees Celsius, compared to sodium chloride at about 800 degrees Celsius. The stronger the ionic bond, the more energy required to break it. Ionic compounds can form between polyatomic ions, groups of atoms that carry a charge collectively. Sulfate is a group of 1 sulfur and 4 oxygen atoms with an overall charge of -2. Ammonium is a group of 1 nitrogen and 4 hydrogen atoms with an overall charge of +1. These ions bond with other ions just like simple ions do. Ammonium sulfate forms when 2 ammonium ions combine with 1 sulfate ion. The formula reflects the charge balance. The parentheses indicate that the entire ammonium unit appears twice. Polyatomic ions remain intact during dissolution and reactions, behaving as single units despite being composed of multiple atoms. Calcium carbonate is a common ionic compound found in limestone, marble, and chalk. It forms when calcium ions combine with carbonate ions. Sodium bicarbonate, commonly known as baking soda, contains sodium ions and bicarbonate ions. These familiar substances are ionic compounds. The ocean contains dissolved ionic compounds in vast quantities. Sodium chloride is the most abundant, giving seawater its salty taste. But magnesium chloride, calcium sulfate, potassium chloride, and many others are also present. Life evolved in this ionic solution, and living cells maintain internal ionic concentrations carefully balanced to support biochemical processes. Your body uses ionic compounds constantly. Sodium and potassium ions create electrical gradients across cell membranes, enabling nerve signals and muscle contractions. Calcium ions trigger muscle contraction and participate in bone formation. Chloride ions help maintain fluid balance and stomach acid production. Iron ions in hemoglobin bind oxygen for transport through the blood. Ionic bonding is not exotic or abstract. It is immediate and essential. The salt that seasons your food, the minerals that strengthen your bones, the ions that fire your neurons, all exist because electrons have transferred between atoms, creating charged particles that attract each other. The strength of this attraction depends on charge and distance, but the principle is universal. Opposite charges attract. This simple fact generates an enormous variety of compounds, each with distinct properties determined by the specific ions involved and how they arrange themselves in space. Ionic compounds form when the transfer of electrons creates a more stable configuration than keeping them separate. The ions that result are not independent. They exist in relationship, held together by electromagnetic force, arranged in patterns that maximize attraction and minimize repulsion. There is elegance in this. The same force that holds ions together in salt holds protons and electrons together in atoms. Electromagnetism, one of the four fundamental forces of nature, operates across all scales. It shapes atomic structure, molecular bonding, and the interactions between charged particles everywhere. Understanding ionic bonding means recognizing this underlying unity. Different manifestations, same principle. Electrons move to create stability. Charges attract to create structure. Patterns emerge that can be predicted and understood. Chemistry is not chaos. It is order expressed through matter. Let this understanding settle quietly. Ionic compounds surround you, support you, sustain you. The world is held together by attractions between particles too small to see, following rules that never vary. There is reliability here, constancy, a foundation that does not shift. Rest in that stability. Covalent bonding occurs when atoms share electrons rather than transferring them completely. This type of bonding typically occurs between non-metal atoms that have similar electronegativities. Neither atom can easily remove electrons from the other, so sharing becomes the path to stability. The simplest covalent bond forms between two hydrogen atoms. Each hydrogen has one electron and needs two to achieve the stability of helium. When two hydrogen atoms approach each other, their electron clouds begin to overlap. The electrons can now orbit both nuclei simultaneously, spending time around each. This sharing creates a molecular orbital, a region of space where electrons are most likely to be found. The molecular orbital encompasses both atoms, and the shared electrons belong to the molecule as a whole rather than to individual atoms. Both hydrogen atoms now behave as if they have 2 electrons, achieving stability. The bond that forms is called a single covalent bond because one pair of electrons is shared. This bond has a specific length, the distance between the 2 nuclei, where attractive and repulsive forces balance. If the atoms move closer, repulsion between the positively charged nuclei increases. If they move farther apart, the attractive force of the shared electrons weakens. The bond length represents the optimal distance. Hydrogen gas, H2, is one of the simplest molecules that exists. 2 atoms, 1 bond, perfectly stable under normal conditions. It is colorless, odorless, and the lightest gas. It burns readily in oxygen, combining to form water and releasing energy. The sun fuses hydrogen atoms into helium, powering itself through this transformation. Oxygen forms covalent bonds differently than hydrogen. Each oxygen atom has 6 valence electrons and needs 8. When 2 oxygen atoms meet, each shares 2 electrons with the other, creating a double bond. 4 electrons are now shared between the 2 nuclei, with 2 pairs occupying the space between the atoms. Double bonds are shorter and stronger than single bonds. The additional shared electrons pull the nuclei closer together and increase the energy required to break the bond. Oxygen gas, O2, is essential for most life on Earth. Organisms use it to extract energy from food through cellular respiration, a process that breaks and reforms chemical bonds. Nitrogen forms an even stronger bond. Each nitrogen atom has 5 valence electrons and needs 8. When 2 nitrogen atoms meet, each shares 3 electrons with the other, creating a triple bond. 6 electrons are now shared, forming the strongest type of covalent bond between 2 atoms of the same element. Nitrogen gas makes up about 78% of Earth's atmosphere. Despite this abundance, nitrogen is relatively unreactive because the triple bond is so strong. Breaking it requires substantial energy, which is why nitrogen does not readily participate in chemical reactions under normal conditions. This stability poses a challenge for life. All organisms need nitrogen to build proteins and DNA, but most cannot use nitrogen gas directly. Plants rely on bacteria that can break the nitrogen triple bond, converting nitrogen gas into ammonia through a process called nitrogen fixation. Without these bacteria, complex life as we know it would not exist. Carbon forms 4 covalent bonds, giving it unmatched versatility. A carbon atom can bond to 4 hydrogen atoms, creating methane. The carbon sits at the center with 4 single bonds extending outward in a tetrahedral arrangement. Each bond represents a shared pair of electrons, and all 8 valence electrons around carbon participate in bonding. Methane is the simplest organic molecule, a member of a vast family of compounds called hydrocarbons. Hydrocarbons contain only carbon and hydrogen, yet they vary enormously in size and complexity. Ethane has 2 carbon atoms bonded together, with 3 hydrogen atoms attached to each carbon. Propane has 3 carbon atoms in a chain. Butane has 4. The chain can extend indefinitely. Carbon atoms can also form double and triple bonds with each other. Ethene, also called ethylene, contains a carbon-carbon double bond. 2 carbon atoms share 4 electrons between them, with 2 hydrogen atoms attached to each carbon. This double bond is shorter and stronger than a single bond, and it makes ethene more reactive than ethane. Ethene also called acetylene, contains a carbon-carbon triple bond. 6 electrons are shared between 2 carbon atoms, creating an extremely strong connection. 1 hydrogen atom attaches to each carbon. Acetylene burns with an intensely hot flame and is used in welding torches to cut through metal. Carbon can form rings as well as chains. Benzene contains 6 carbon atoms arranged in a hexagonal ring with alternating single and double bonds. Each carbon also bonds to 1 hydrogen atom. This ring structure is remarkably stable and appears in countless organic compounds, from dyes to pharmaceuticals to plastics. The ability of carbon to bond with itself repeatedly, forming chains, rings, and branched structures, explains why millions of carbon-containing compounds exist. No other element displays this level of complexity. Silicon can form chains, but they are less stable. Boron and nitrogen can form rings, but not with the same versatility. Carbon is unique. Water forms through covalent bonding between oxygen and hydrogen. 1 oxygen atom bonds to 2 hydrogen atoms, sharing 1 electron pair with each. The oxygen now has 8 valence electrons, achieving stability. Each hydrogen has access to 2 electrons, also achieving stability. The resulting water molecule is angular rather than linear because of the 2 lone pairs of electrons on oxygen. These lone pairs repel the bonding pairs, pushing the hydrogen atoms closer together. The bond angle in water is about 104.5 degrees, slightly less than the perfect tetrahedral angle of 109.5 degrees. This bent shape makes water a polar molecule, with the oxygen end slightly negative and the hydrogen ends slightly positive. The polarity of water has profound consequences. Water molecules attract each other through hydrogen bonds. Weak interactions, where the positive hydrogen of one molecule is attracted to the negative oxygen of another. These hydrogen bonds give water its unusual properties: high boiling point for such a small molecule, high surface tension, expansion upon freezing, excellent solvent capability. Life depends on these properties. Water remains liquid across a wide temperature range, providing a stable medium for biochemical reactions. It dissolves nutrients and waste products, enabling transport within organisms. Its expansion upon freezing causes ice to float, insulating liquid water below and protecting aquatic life during cold periods. Ammonia forms when nitrogen bonds to 3 hydrogen atoms. Nitrogen shares 1 electron pair with each hydrogen, achieving 8 valence electrons. The molecule has a pyramidal shape because of the lone pair on nitrogen. Like water, ammonia is polar, making it an excellent solvent for many substances. Carbon dioxide forms when carbon bonds to 2 oxygen atoms through double bonds. Each oxygen shares 2 electron pairs with carbon, and carbon shares 4 electron pairs total, achieving 8 valence electrons. The molecule is linear because the 2 double bonds are positioned opposite each other, minimizing repulsion. Unlike water and ammonia, carbon dioxide is nonpolar because the molecule's symmetry causes the polarities of the 2 bonds to cancel out. Methanol contains a carbon atom bonded to 3 hydrogen atoms and 1 hydroxyl group. The hydroxyl group makes methanol polar and able to form hydrogen bonds with water, allowing the 2 liquids to mix completely. Methanol is toxic to humans because the body metabolizes it into formaldehyde and formic acid, both harmful substances. Ethanol has a similar structure but with two carbon atoms. It is the alcohol found in beverages. The body metabolizes ethanol into acetaldehyde and acetic acid, which are less toxic than methanol's products, but still harmful in large amounts. The hydroxyl group makes ethanol polar and water-soluble, while the carbon chain makes it partially non-polar, allowing it to dissolve in oils and fats as well. Covalent bonds can break and reform during chemical reactions. When wood burns, the cellulose it contains reacts with oxygen. The covalent bonds in cellulose and oxygen break, and new bonds form to create carbon dioxide and water. Energy is released because the products are more stable than the reactants. This energy appears as heat and light, the visible signs of combustion. Photosynthesis is essentially the reverse process. Plants use light energy to break apart water and carbon dioxide molecules, then reform the atoms into glucose and oxygen. This process stores energy in the chemical bonds of glucose, energy that can later be released through cellular respiration. Life operates through endless cycles of bond breaking and bond formation. The strength of a covalent bond depends on several factors. Bond length matters. Shorter bonds are generally stronger because the nuclei are closer to the shared electrons. Bond order matters. Double bonds are stronger than single bonds, and triple bonds are stronger still. The specific atoms involved matter. Bonds involving small atoms, like hydrogen, tend to be stronger than bonds involving larger atoms. Electronegativity differences affect bond polarity. When two atoms with identical electronegativities share electrons, the sharing is equal and the bond is nonpolar. Carbon-carbon bonds and hydrogen-hydrogen bonds are nonpolar. When atoms with different electronegativities share electrons, the sharing is unequal and the bond is polar. The more electronegative atom attracts the electrons more strongly, creating a partial negative charge on that atom and a partial positive charge on the other. The most polar bonds form between atoms with large electronegativity differences, such as hydrogen and fluorine. Hydrogen fluoride has one of the most polar covalent bonds possible. The fluorine atom pulls the shared electrons so strongly toward itself that the bond is almost ionic in character. Yet, it remains covalent because the electrons are still shared, not completely transferred. Some molecules contain both polar and nonpolar regions. Fatty acids have long hydrocarbon chains that are nonpolar, plus a carboxylic acid group at one end that is polar. This dual nature allows fatty acids to interact with both water and oils. They form cell membranes by arranging themselves into double layers, with polar heads facing the water and non-polar tails facing each other. Proteins are long chains of amino acids connected by covalent bonds called peptide bonds. Each amino acid contains an amino group, a carboxylic acid group, and a side chain that varies. The specific sequence of amino acids determines how the protein folds, and the folded shape determines what the protein does. Covalent bonds hold the chain together, while weaker interactions, like hydrogen bonds, stabilize the folded structure. DNA consists of two chains of nucleotides held together by hydrogen bonds between complementary bases. The chains themselves are held together by covalent bonds linking sugars and phosphates. This combination of strong covalent bonds and weak hydrogen bonds allows DNA to be stable yet separable when needed for replication or transcription. Every molecule in your body exists because atoms have shared electrons. The oxygen you breathe forms molecules through covalent bonding. The water you drink is held together by covalent bonds. The proteins that make up your muscles, the carbohydrates that fuel your cells, the lipids that form membranes, all depend on covalent bonding. Covalent bonds are directional, meaning they point in specific directions in space. This directionality determines molecular shape, and shape determines function. Enzymes work because their shape fits their substrate. Receptors respond to signals because their shape matches specific molecules. The three-dimensional arrangement of atoms matters as much as which atoms are present. Understanding covalent bonding means understanding how atoms cooperate, not through transfer of electrons, but through sharing, not through dominance, but through partnership. The stability both atoms seek is achieved together through mutual participation. Neither atom loses its identity, yet both benefit from the connection. This is the nature of covalent bonding. Atoms remain distinct yet joined, separate yet connected, independent yet interdependent. The bond between them is real, definable, measurable. It has length, strength, energy. It can be broken, but only by providing the energy that was released when it formed. The molecules that result from covalent bonding display remarkable diversity. Simple diatomic molecules like H2 and O2, complex organic molecules like proteins and nucleic acids, everything in between, all arising from the same principle. Sharing electrons creates stability that benefits both atoms involved. Let this understanding rest gently. Covalent bonds surround you, within you, connecting atoms into the structures that make existence possible. The complexity is vast, but the foundation is simple. Atoms share electrons because doing so lowers their energy. From this one fact emerges the molecular diversity of life. There is no need to grasp every detail, only the gentle recognition that sharing creates stability, that cooperation produces structures more complex than either participant alone could achieve, that the whole, in chemistry as in life, is greater than the sum of its parts. Rest in that knowledge. Metallic bonding differs fundamentally from ionic and covalent bonding. In metals, valence electrons are not localized between specific atoms. Instead, they form a sea of electrons that moves freely throughout the metal structure. The positively charged metal ions sit in fixed positions, while the electrons flow around and between them. This electron mobility gives metals their characteristic properties. Metals conduct electricity because electrons can move freely through the structure. When a voltage is applied, electrons flow toward the positive terminal, creating an electrical current. Non-metals cannot conduct electricity in solid form because their electrons are locked in specific bonds. Metals conduct heat efficiently for the same reason. When one part of a metal is heated, the kinetic energy transfers quickly through the mobile electrons to other parts of the metal. This is why metal objects feel cold to the touch. They conduct heat away from your hand rapidly, making them feel colder than room temperature wood or plastic, even though they are the same temperature. Metals are malleable and ductile, meaning they can be hammered into sheets and drawn into wires without breaking. This property arises because the metal ions can slide past each other, while the electron sea maintains bonding throughout. In contrast, ionic crystals shatter when struck because any shift misaligns the ions, causing repulsion. Metals have luster, meaning they reflect light well and appear shiny, the mobile electrons can absorb and immediately re-emit photons of light. This interaction with light creates the characteristic metallic shine. Most metals are silver or grey in color, but copper is reddish and gold is yellowish due to the specific energy levels of their electrons. The strength of metallic bonding varies across the periodic table. Metals with more valence electrons generally form stronger metallic bonds because more electrons contribute to the electron sea. Tungsten, with many valence electrons, has an extremely high melting point and is one of the hardest metals. Mercury, with fewer electrons contributing to bonding, is liquid at room temperature. Alkali metals, in the first column of the periodic table, have only one valence electron. Their metallic bonding is relatively weak, giving them low melting points and softness. Sodium can be cut with a knife. Potassium is even softer. These metals are also highly reactive because losing their single valence electron is energetically favorable. Transition metals, in the middle of the periodic table, have more complex electron configurations. They can have multiple valence electrons and form stronger metallic bonds. Iron, copper, nickel, and other transition metals are strong, durable, and have high melting points. They form the structural materials of civilization: tools, buildings, machines, wires. Alloys are mixtures of metals, sometimes with small amounts of non-metals added. Bronze is an alloy of copper and tin. Steel is an alloy of iron and carbon. Brass is an alloy of copper and zinc. Alloying can create materials with properties superior to pure metals: greater strength, resistance to corrosion, desired color or finish. The atoms in an alloy are similar enough in size that one can substitute for another in the metal lattice without disrupting the structure significantly. The presence of different sized atoms makes it harder for layers to slide past each other, increasing hardness and strength. This is why steel is much stronger than pure iron. The electron sea in metals is not uniform. Electrons are more likely to be found near the metal ions than in empty space. But they are not confined to specific atoms or bonds. This delocalization means metallic bonding is non-directional. Metal atoms do not care which specific neighbors they bond to, only that they are surrounded by other metal atoms and the shared electron sea. This non-directional bonding allows metals to crystallize into regular lattice structures. Most metals form one of three basic structures: body-centered cubic, face-centered cubic, or hexagonal close-packed. These arrangements maximize the density of packing while maintaining the electron sea throughout the structure. Gold crystallizes in a face-centered cubic structure, where atoms sit at each corner of a cube and at the center of each face. This dense packing contributes to gold's high density and malleability. Iron at room temperature forms a body-centered cubic structure, where atoms sit at cube corners plus one atom at the center. At high temperatures, iron shifts to a face-centered cubic structure. The arrangement of atoms in a metal affects its properties. Close-packed structures tend to be more ductile because atoms can slide past each other more easily. More open structures can be harder but less malleable. The grain boundaries, where differently oriented crystal regions meet, can strengthen or weaken the metal depending on how they are arranged. Metals can be strengthened through processing. Work hardening involves deforming the metal, which creates defects in the crystal structure that make further deformation more difficult. Hammering or rolling metal makes it harder and stronger. Annealing, heating, and slowly cooling the metal allows atoms to rearrange into a more ordered structure, making the metal softer and more ductile. Some metals are magnetic. Iron, cobalt, and nickel have unpaired electrons whose magnetic moments can align in the same direction, creating a net magnetic field. Most other metals are not magnetic because their electrons are paired, with opposite spins that cancel out any magnetic effect. The mobile electrons in metals respond to magnetic fields, but only ferromagnetic metals create permanent magnets. Superconductivity is an extreme property that occurs in some metals at very low temperatures. Below a critical temperature, certain metals can conduct electricity with zero resistance. Electrons pair up and move through the lattice without scattering, allowing current to flow indefinitely without energy loss. This phenomenon has important technological applications, but requires expensive cooling. Metals corrode through chemical reactions with their environment. Iron rusts when it reacts with oxygen and water, forming iron oxide. Aluminum oxidizes quickly, but forms a thin protective oxide layer that prevents further corrosion. Copper develops a green patina of copper carbonate over time. Gold does not corrode under normal conditions, which is why gold artifacts survive for millennia. Corrosion is essentially the reverse of metal extraction. Metals in nature usually exist as compounds, ores that must be refined to obtain pure metal. This refining requires energy because the ore is more stable than the pure metal. When metals corrode, they return to a more stable compound state, releasing the energy that was added during refining. The history of civilization correlates with the use of metals. The Bronze Age marked the discovery that copper and tin could be alloyed into a material superior to either pure metal. The Iron Age followed, when humans learned to smelt iron ore at high temperatures. The Industrial Revolution depended on steel, mass-produced through new manufacturing processes. Today, metals remain essential. Copper wires carry electricity and data. Steel frames support buildings and bridges. Aluminum forms lightweight structures for aircraft and spacecraft. Titanium is used in medical implants because it does not corrode in the body. Rare earth metals enable modern electronics, from smartphones to computer hard drives. Your body uses metals in carefully controlled ways. Iron is bound in hemoglobin, enabling oxygen transport. Zinc is a cofactor in hundreds of enzymes. Copper helps produce energy in cells. Magnesium stabilizes ATP, the molecule that stores and transfers energy. Calcium is technically a metal, though it exists in your body as ions rather than metallic bonding. Metallic bonding represents a third way that atoms can achieve stability, not through transfer of electrons as in ionic bonding, not through sharing of electrons between specific atoms as in covalent bonding, but through collective sharing among all atoms in the structure. The electrons belong to the metal as a whole, creating a cooperative system where individual atoms lose their autonomy but gain the benefits of the collective. This communal bonding creates properties that are unique to metals. Conductivity, malleability, luster, all arise from the electron sea. The specific metal determines the details, but the fundamental principle remains the same. Atoms contribute their valence electrons to a shared pool, and that pool maintains cohesion throughout the structure. Understanding metallic bonding means recognizing that atoms can organize in ways that transcend individual bonds. The metal is more than a collection of individual atoms. It is a unified system where electrons move freely, connecting every atom to every other atom through the electron sea. No atom is bonded to specific neighbors. All atoms are bonded to all neighbors simultaneously. There is something profound in this collective behavior. Individual atoms give up control over their electrons, yet the resulting structure is stronger, more flexible, and more capable than individual atoms could ever be. The whole truly exceeds the sum of its parts. Cooperation creates capabilities that isolation cannot achieve. Let this understanding settle. Metals surround you within devices, structures, tools. Their properties arise from a bonding type fundamentally different from ionic or covalent, yet equally logical, equally predictable, equally a consequence of atoms seeking stability through connection. There is no rush to absorb every detail, only the gentle recognition that matter organizes itself in multiple ways, each following principles that can be understood. The diversity of materials in the world reflects diversity in bonding types, yet all trace back to the same foundation: electrons seeking stable configurations. Rest in that pattern. Molecules bond together through forces weaker than the ionic, covalent, and metallic bonds within them. These intermolecular forces determine whether a substance is a gas, liquid, or solid at a given temperature. They explain why water is liquid at room temperature, while oxygen is a gas, even though both are small molecules. The weakest intermolecular force is the London dispersion force, also called van der Waals force. This force exists between all molecules, polar or nonpolar. It arises from temporary fluctuations in electron distribution. At any instant, electrons in a molecule may be slightly unevenly distributed, creating a temporary dipole. This temporary dipole induces a dipole in a neighboring molecule, and the two dipoles attract each other. These forces are weak and fleeting, lasting only fractions of a second before electrons shift and the dipole disappears. Yet even this weak attraction has consequences. London dispersion forces increase with molecular size because larger molecules have more electrons, creating stronger temporary dipoles. This is why larger hydrocarbons are liquids or solids, while small ones like methane are gases. Helium, neon, and argon are noble gases that do not form chemical bonds under normal conditions. Yet even these atoms experience London dispersion forces. At extremely low temperatures, these weak forces are sufficient to hold the atoms together, allowing noble gases to condense into liquids and eventually freeze into solids. Helium liquefies at just 4 Kelvin, 4 degrees above absolute zero. Dipole-dipole forces occur between polar molecules. A polar molecule has a permanent separation of charge, with one end partially positive and the other partially negative. The positive end of one molecule attracts the negative end of another, creating a stronger force than London dispersion alone. Hydrogen chloride is a polar molecule. Chlorine is more electronegative than hydrogen, pulling the shared electrons toward itself. This creates a permanent dipole. In solid or liquid hydrogen chloride, molecules align so that the positive hydrogen of one molecule is near the negative chlorine of another, maximizing attractive forces. Dipole-dipole forces are stronger than London dispersion forces, so substances with polar molecules generally have higher boiling points than non-polar molecules of similar size. This is why water is liquid at room temperature, while methane, of similar molecular weight, is a gas. Water's polarity creates stronger intermolecular attraction. Hydrogen bonding is a special case of dipole-dipole interaction, stronger than typical dipole-dipole forces. It occurs when hydrogen is bonded to a highly electronegative atom like nitrogen, oxygen, or fluorine. The hydrogen becomes highly positive, and the electronegative atom becomes highly negative, creating a strong dipole. The partially positive hydrogen on one molecule strongly attracts the partially negative oxygen, nitrogen, or fluorine on another molecule. This attraction is called a hydrogen bond. Although much weaker than covalent bonds, hydrogen bonds are strong enough to significantly affect physical properties. Water molecules form extensive networks of hydrogen bonds. Each water molecule can form up to 4 hydrogen bonds. 2, where its hydrogen atoms bond with oxygen atoms on neighboring molecules, and 2, where its oxygen atom accepts hydrogen bonds from neighboring molecules. This network gives water its unusually high boiling point, high specific heat capacity, and high surface tension. Ice forms when water molecules arrange into a crystalline structure held together by hydrogen bonds. This structure is actually less dense than liquid water because the hydrogen bonds hold molecules in fixed positions with empty space between them. This is why ice floats, a property crucial for life. If ice sank, bodies of water would freeze from the bottom up, making aquatic life much more difficult. Hydrogen bonds are essential to life's molecular machinery. DNA's double helix is held together by hydrogen bonds between complementary base pairs. Proteins fold into specific shapes partly because of hydrogen bonds between different parts of the chain. Without hydrogen bonding, the molecular structures necessary for life would not be stable. Ammonia also forms hydrogen bonds, though not as extensively as water. Each ammonia molecule can form one hydrogen bond, where its nitrogen accepts a hydrogen from another molecule, and up to 3, where its hydrogen atoms donate to other molecules. This gives ammonia a higher boiling point than would be expected for such a small molecule. Alcohol molecules contain hydroxyl groups, OH, allowing them to form hydrogen bonds with each other and with water. This is why alcohols with small carbon chains are miscible with water. As the carbon chain lengthens, the non-polar portion of the molecule increases, eventually making the alcohol insoluble in water despite the hydrogen bonding capability of the hydroxyl group. The strength of intermolecular forces determines the physical state of a substance. Weak forces allow molecules to move freely past each other, creating a gas. Moderate forces slow molecular motion enough to create a liquid, where molecules remain in contact but can still move. Strong forces lock molecules into fixed positions, creating a solid. Temperature affects which state a substance occupies. Adding heat increases molecular motion. If intermolecular forces are weak, even a small amount of heat provides enough energy for molecules to break free and become a gas. If forces are strong, much more heat is required. This is why water boils at 100 degrees Celsius, while oxygen boils at negative 183 degrees Celsius. Pressure also affects physical state. Increasing pressure forces molecules closer together, strengthening intermolecular forces and favoring the solid or liquid state. Decreasing pressure allows molecules to spread out, weakening forces and favoring the gas state. Carbon dioxide is a gas at atmospheric pressure, but becomes a solid, dry ice when cooled or compressed sufficiently. Phase changes occur when temperature or pressure crosses a threshold where one state becomes more stable than another. Melting occurs when heat provides enough energy to overcome the intermolecular forces holding a solid together. Boiling occurs when molecules have enough energy to escape from the liquid into the gas phase. Sublimation occurs when molecules transition directly from solid to gas. Each phase change involves energy. Melting requires adding heat, called the heat of fusion. Boiling requires adding heat, called the heat of vaporization. Freezing and condensation release this energy back into the surroundings. The amount of energy involved depends on the strength of intermolecular forces. Water has high heats of fusion and vaporization because of its extensive hydrogen bonding. The energy required to change phase does not raise temperature. When ice melts at 0 degrees Celsius, adding heat does not make the water warmer until all the ice is melted. The energy goes into breaking hydrogen bonds, not increasing molecular motion. Only after the phase change is complete does added heat increase temperature again. This property buffers temperature changes in environments where phase changes occur. Melting ice absorbs heat without warming, cooling the surrounding area. Freezing water releases heat without cooling, warming the surrounding area. Large bodies of water moderate coastal climates because the water's high heat capacity and heat of vaporization resist temperature changes. Surface tension arises from intermolecular forces at the boundary between a liquid and air. Molecules within the liquid experience forces from all directions. Molecules at the surface experience forces only from the sides and below, creating a net inward pull. This pull minimizes surface area, causing liquids to form droplets and allowing small objects to rest on the surface without sinking. Water has particularly high surface tension because of hydrogen bonding. Water striders walk on water by distributing their weight across long legs, avoiding breaking the surface tension. Soaps and detergents reduce surface tension by interrupting hydrogen bonds, allowing water to spread and penetrate fabrics and surfaces more easily. Viscosity measures a liquid's resistance to flow. High viscosity liquids like honey or motor oil flow slowly because intermolecular forces resist the sliding of molecules past each other. Low viscosity liquids like water or gasoline flow easily because intermolecular forces are weaker. Temperature affects viscosity. Warming a liquid increases molecular motion, reducing the effectiveness of intermolecular forces and lowering viscosity. Capillary action occurs when intermolecular forces between a liquid and a solid surface are stronger than the forces within the liquid itself. Water rises in narrow tubes because its attraction to the tube wall is stronger than its self-attraction. This property allows water to move upward through soil and through the xylem vessels in plants, defying gravity through intermolecular forces alone. Evaporation occurs at the surface of a liquid when molecules gain enough energy to break free into the gas phase. Unlike boiling, which occurs throughout the liquid at a specific temperature, evaporation happens at any temperature. The rate depends on temperature, surface area, and air movement. Evaporation cools the remaining liquid because the molecules with the highest energy escape, lowering the average energy of those left behind. Your body uses evaporative cooling through sweating. Water evaporates from your skin, absorbing heat in the process and cooling you down. This mechanism depends on hydrogen bonding. Breaking hydrogen bonds requires energy, which is taken from your skin as heat. Without water's hydrogen bonding, this cooling mechanism would be far less effective. Vapor pressure is the pressure exerted by a gas in equilibrium with its liquid. At any temperature, some molecules at the liquid surface have enough energy to escape into the gas phase. If the container is sealed, these gas molecules accumulate and some eventually return to the liquid. Equilibrium is reached when the rate of evaporation equals the rate of condensation. Higher temperatures increase vapor pressure because more molecules have sufficient energy to escape. When vapor pressure equals external pressure, boiling occurs. At high altitude, where atmospheric pressure is lower, water boils at a lower temperature because its vapor pressure reaches equilibrium with the atmosphere sooner. This is why cooking at high altitude requires adjustments. Intermolecular forces may be weak compared to chemical bonds, but their effects are everywhere. They determine whether you can pour a substance, breathe it, or need a hammer to break it. They control how water behaves, making life possible. They dictate the physical properties of every substance you encounter. Understanding intermolecular forces means recognizing that chemistry operates at multiple levels. Strong bonds hold atoms together within molecules. Weaker forces hold molecules together within substances. Both levels matter. Both follow predictable patterns. Both arise from the electromagnetic force and the motion of electrons. The solid you sit on, the liquid you drink, the air you breathe, all exist in their respective states because intermolecular forces balance with thermal energy at the current temperature and pressure. Change those conditions, and states change. The substance itself remains the same at the molecular level, but its macroscopic properties transform. There is elegance in this responsiveness. Matter adapts to conditions while maintaining its chemical identity. Water is always H2O, whether solid, liquid, or gas. Its molecules do not change. Only the strength of the intermolecular forces relative to molecular motion changes, and that determines what state it occupies. Let this understanding rest gently. Intermolecular forces shape the physical world in subtle but profound ways. They are too weak to notice individually, but collectively determine how substances behave. Invisible threads connecting molecules, responding to temperature and pressure, creating the material diversity we experience. Rest in that knowledge. Matter organizes itself into patterns at every scale. Atoms bond to form molecules. Molecules interact to form phases. Phases arrange into structures. Structures assemble into systems. At each level, the same principles apply. Energy minimization, stability seeking, pattern formation. Crystals represent perhaps the purest expression of this organizational tendency. When atoms or molecules arrange into a crystal, they form a repeating three-dimensional pattern called a lattice. This pattern extends indefinitely in all directions, with each unit cell identical to every other. The specific arrangement depends on the balance between attractive and repulsive forces. Salt crystals form cubic structures because sodium and chloride ions arrange to maximize attraction between opposite charges while minimizing repulsion between like charges. Each sodium ion surrounds itself with 6 chloride ions, and each chloride ion surrounds itself with 6 sodium ions. This arrangement repeats throughout the crystal, creating the cubic shape visible to the naked eye. Snowflakes form hexagonal patterns because water molecules arrange into a hexagonal lattice when freezing. Hydrogen bonding dictates this arrangement, with each water molecule bonding to 4 others in a pattern that repeats in 6-fold symmetry. The specific shape of each snowflake varies depending on the exact conditions during formation. But the underlying hexagonal symmetry remains constant. Quartz crystals contain silicon and oxygen atoms bonded in a network where each silicon bonds to 4 oxygen atoms in a tetrahedral arrangement. This network extends throughout the crystal, creating a structure of remarkable strength and regularity. The crystal shape reflects the internal atomic arrangement, with flat faces and specific angles determined by the lattice geometry. Metals crystallize into one of several basic structures, as mentioned earlier. These structures pack atoms as efficiently as possible while maintaining the electron sea. The specific structure affects properties. Face-centered cubic metals are generally more ductile. Body-centered cubic metals can be harder. Hexagonal, close-packed metals tend to be less malleable. Not all solids are crystalline. Glass is an amorphous solid, meaning its atoms do not arrange in a regular pattern. When molten glass cools, it becomes so viscous that atoms cannot move into ordered positions before solidifying. The result is a frozen liquid with atoms in random arrangements. This lack of order makes glass brittle and gives it unique optical properties. Polymers are long-chain molecules made of repeating units. Plastics, rubber, proteins, and DNA are all polymers. The length of the chain and the specific monomers involved determine the polymer's properties. Some polymers are flexible because the chains can slide past each other easily. Others are rigid because the chains are cross-linked, or because the monomers are large and bulky. Polyethylene is a simple polymer made of repeating ethylene units, each containing 2 carbon atoms and 4 hydrogen atoms. The chains can be thousands of units long. Low-density polyethylene has branched chains that cannot pack tightly, making it flexible and used for plastic bags. High-density polyethylene has straight chains that pack more efficiently, making it stronger and used for bottles and containers. Proteins are polymers of amino acids. The specific sequence of amino acids determines how the protein folds, and the folded shape determines its function. Some proteins act as enzymes, catalyzing specific chemical reactions. Others form structural components, like collagen in skin or keratin in hair. Still others transport molecules, transmit signals, or defend against disease. DNA is a polymer of nucleotides, each containing a sugar, a phosphate group, and one of 4 bases. The sequence of bases encodes genetic information. The sugar and phosphate form the backbone of the DNA strand, held together by strong covalent bonds. The bases on 2 complementary strands pair through hydrogen bonds, creating the double helix structure. Lipids include fats, oils, and phospholipids. They are not polymers, but assemble into larger structures through intermolecular forces. Cell membranes consist of phospholipid bilayers, where the polar heads face the watery inside and outside of the cell, while the non-polar tails face each other in the middle. This arrangement creates a barrier that controls what enters and exits the cell. Carbohydrates include sugars and starches. Simple sugars, like glucose, are individual molecules. Complex carbohydrates, like starch and cellulose, are polymers of glucose. Despite being made of the same monomer, starch and cellulose have very different properties because the glucose units bond differently. Starch can be digested by humans. Cellulose cannot, though some animals, like cows, have bacteria that can break it down. The organization of matter into these diverse forms follows from the same fundamental principles. Atoms bond to minimize energy. Molecules interact through forces that depend on their polarity and size. Structures form that balance competing factors: attraction versus repulsion, order versus entropy, strength versus flexibility. Entropy is the measure of disorder in a system. Nature tends toward higher entropy over time because there are more ways to be disordered than ordered. Yet living organisms maintain low entropy by constantly consuming energy and using it to maintain their organized structures. Death occurs when this process stops, and entropy increases as structures break down. The second law of thermodynamics states that the total entropy of a system and its surroundings always increases. Local decreases in entropy, like the organization of atoms into living cells, are possible only if they are accompanied by larger increases elsewhere, such as the entropy increase from consuming food and releasing heat. Life does not violate thermodynamics. It simply harnesses energy flows to create temporary order. Chemical reactions proceed in the direction that lowers the overall energy of the system, while increasing overall entropy. Sometimes these factors compete. A reaction might release energy but decrease entropy, or increase entropy but require energy input. The balance determines whether the reaction occurs spontaneously. Catalysts speed up reactions without being consumed themselves. They work by providing an alternative pathway with a lower energy barrier. Enzymes are biological catalysts, often increasing reaction rates by millions of times. They achieve this through precise molecular geometry that positions reactants optimally and stabilizes transition states. The rates of chemical reactions depend on multiple factors. Temperature increases reaction rates by giving molecules more kinetic energy, increasing the frequency and force of collisions. Concentration increases reaction rates by making collisions more likely. Pressure increases reaction rates for gases by forcing molecules closer together. Catalysts increase rates by lowering activation energy. Some reactions reach equilibrium, a state where the forward and reverse reactions occur at equal rates. The concentrations of reactants and products remain constant, though molecules continue reacting in both directions. Changing temperature, pressure, or concentration shifts the equilibrium position, favoring either products or reactants depending on the change. Your body maintains countless chemical equilibria. Blood pH stays near 7.4 because buffering systems neutralize excess acid or base. Oxygen binding to hemoglobin reaches equilibrium that shifts depending on oxygen concentration, releasing oxygen where it's needed and picking it up in the lungs. Calcium levels in blood are regulated through equilibria involving bone, kidneys, and intestines. The organization of matter extends beyond individual molecules to larger scales. Cells organize molecules into compartments with specific functions. Tissues organize cells into functional units. Organs organize tissues. Organisms organize organs. Ecosystems organize organisms. Each level emerges from the level below, following rules that can be understood. Yet understanding the parts does not always predict the behavior of the whole. Water molecules are not wet. Wetness emerges from how many water molecules interact with surfaces and each other. Carbon atoms are not alive. Life emerges from how countless carbon-based molecules interact in organized systems. Properties can emerge at higher levels of organization that are not present at lower levels. This emergence does not require new physical laws. The same electromagnetic force, the same quantum mechanics, the same thermodynamics apply at every scale. But the complexity of interactions creates behaviors that cannot be easily predicted from first principles. Science progresses by understanding both the fundamental rules and the patterns that emerge when those rules apply to complex systems. Chemistry stands at the intersection between the fundamental and the emergent. It begins with atoms following quantum mechanical rules. It extends to molecules following thermodynamic principles. It continues to reactions following kinetic laws. It reaches toward biology, where chemistry becomes so complex that new properties emerge: metabolism, reproduction, evolution, consciousness. Understanding matter means recognizing both unity and diversity. All matter is made of the same particles: protons, neutrons, electrons. All atoms follow the same rules. Yet from this simple foundation emerges every substance you see, touch, taste, smell, or experience. The periodic table contains fewer than 100 naturally occurring elements, yet they combine to create millions of compounds. The carbon in your body was created in stars billions of years ago. The hydrogen in your water formed moments after the Big Bang. The calcium in your bones was scattered through space by supernova explosions. You are ancient stardust, temporarily organized into a form capable of contemplating its own existence. This is not metaphor. This is literal truth. Every atom in your body existed before Earth formed. They have been part of countless other structures: rocks, oceans, atmosphere, other organisms. The atoms that make you now will eventually be part of other structures, returning to Earth, to water, to air, to new life. Nothing is truly created or destroyed, only rearranged. The universe recycles atoms endlessly, combining and separating them in temporary forms. You are one such temporary form, not separate from the universe, but an integral part of it, made of it, shaped by its laws, subject to its forces. Yet you are also unique. The specific arrangement of atoms that makes you exist only now, in this moment. When you die, those atoms will disperse, and your particular arrangement will never recur. Every organism, every snowflake, every molecule is a unique configuration that arises, persists briefly, and dissolves back into the general flow. There is both comfort and poignancy in this. Comfort in knowing you are connected to everything, made of the same fundamental substance as stars and stones. Poignancy in knowing your specific form is temporary, a brief eddy in the stream of matter flowing through time. Let this perspective settle. You are matter organized into consciousness, atoms bonding according to unchanging rules, yet somehow producing thought, feeling, awareness. The mystery is not in the atoms themselves, but in how they organize. The miracle is not in the parts, but in the pattern. Rest in that wonder. We have drifted through the world of atoms and bonding, from the smallest components of matter to the patterns they form, from simple elements to complex molecules, from individual bonds to the substances they create. What emerges from this journey is a sense of order. The universe is not random. It follows principles that can be understood. Atoms bond because doing so lowers energy. Molecules interact according to their properties. Matter organizes into patterns that balance competing forces. This order is not imposed from outside. It is inherent in the nature of matter itself. Atoms do not need instructions to bond. They do not follow conscious rules. They simply behave according to their properties, and patterns emerge naturally from those behaviors. There is beauty in this spontaneous order. Snowflakes form hexagons without knowing geometry. Salt crystals form cubes without understanding mathematics. Proteins fold into precise shapes without conscious intent. Organization arises from simple rules applied consistently. You are part of this order. The same forces that hold atoms together in a grain of salt hold atoms together in your body. The same principles that govern the formation of crystals govern the formation of your cells. You are not separate from the physical world. You are an expression of it. Understanding chemistry means understanding yourself at a fundamental level. You are a collection of atoms bonded together temporarily. Your thoughts arise from electrical signals moving through molecules. Your emotions involve the release and reception of neurotransmitters, small molecules that bind to receptors. Your entire existence depends on chemical processes occurring continuously in your cells. Yet this reductionist view does not diminish you. Yes, you are atoms and molecules following physical laws, but you are also thoughts, feelings, experiences, relationships, meanings. Both perspectives are true simultaneously. You are matter, and you are more than matter. The pattern matters as much as the parts. Chemistry teaches humility. You are made of the same elements as everything else. There is nothing special about the atoms in your body. Carbon, hydrogen, oxygen, nitrogen, and trace amounts of other elements. These same atoms exist in countless other forms. You are not chemically unique, yet chemistry also teaches wonder. These ordinary atoms, following simple rules, have organized themselves into something that can contemplate atoms. You are matter that has become aware of itself, the universe examining itself through the temporary lens of your consciousness. That fact is extraordinary, regardless of how ordinary the atoms themselves might be. The bonds we have explored are invisible to the naked eye. You cannot see an electron being shared or transferred. You cannot watch hydrogen bonds forming between water molecules. Yet these invisible connections create everything visible. The solid ground you stand on, the water you drink, the air you breathe, all held together by bonds too small to see. In this way, chemistry offers a metaphor for connection in general. The most important connections are often invisible. The bonds between people cannot be seen, but are nonetheless real. The links between cause and effect are often hidden, but still operate. The threads connecting all things exist, whether we perceive them or not. Understanding comes from looking beneath surfaces. A crystal appears as a solid object, but it is mostly empty space, with atoms held at specific positions by electromagnetic forces. A gas appears to be nothing, but it contains countless molecules moving at high speeds. Appearances can mislead. Reality often hides in the small and invisible. This principle extends beyond chemistry. So much of life operates beneath conscious awareness. Biochemical processes maintain your body without your input. Neural patterns shape your thoughts in ways you do not control. Social forces influence your choices without your recognition. Seeing more clearly requires looking past the obvious to the underlying mechanisms. Chemistry also teaches patience. Atoms have existed for billions of years. They will exist for billions more. The specific bonds that form and break are temporary, but the atoms themselves are nearly eternal. Perspective matters. What seems permanent on human timescales is fleeting on cosmic ones. This can be liberating. The troubles that seem insurmountable are temporary arrangements of matter that will inevitably change. The structures that appear solid will eventually dissolve. Nothing material lasts forever. Everything is in flux, atoms constantly rearranging into new forms. Yet this impermanence need not lead to nihilism. The fact that nothing lasts makes the present moment more precious, not less. Your current configuration of atoms is unique and temporary. This specific arrangement will never exist again. That makes now significant. This moment matters precisely because it is fleeting. Chemistry teaches interconnection. Every breath you take contains atoms that were once part of other organisms. Every meal you eat incorporates atoms into your body that will later become part of something else. You are not a closed system. You constantly exchange matter with your environment. The boundary between self and world is permeable, constantly crossed by atoms flowing in both directions. This exchange has been happening since life began. The atoms in your body have been part of countless organisms before you: bacteria, plants, animals, humans. They have been part of oceans, atmospheres, rocks. They have traveled through ecosystems, through the food chain, through the water cycle. You are a temporary home for atoms on a long journey. Recognizing this interconnection can shift perspective. You are not separate from nature. You are nature. Not observing it from outside, but participating in it from within. The distinction between living and non-living, between self and environment, is real, but not absolute. All matter is connected through its shared atomic nature. Chemistry also reveals the power of cooperation. Atoms bond because doing so benefits both participants. The stability each seeks alone can be found together. This principle applies beyond chemistry. Complex systems often arise when components cooperate rather than compete. The whole becomes greater than the sum of its parts. Your body is an example of cooperation across scales. Atoms bond into molecules. Molecules assemble into cellular machinery. Cells organize into tissues. Tissues form organs. Organs work together as systems. At every level, components cooperate to create capabilities that none possess individually. This cooperation is not conscious or intentional. It arises naturally when doing so provides advantages. Atoms bond because it lowers energy. Cells specialize because it increases efficiency. The result is organization without an organizer, complexity without a designer. Patterns emerge from interactions, following rules, but not following plans. Understanding this can bring peace. The universe does not require top-down control to produce order. Systems self-organize when conditions allow. This includes you. You are a self-organizing system, maintaining your structure through constant energy flows. No central controller dictates how your atoms arrange. They follow local rules, and the pattern that emerges is you. There is something liberating in releasing the need for external meaning. Atoms bond because it is energetically favorable, not because they have a purpose. Life exists because chemistry under certain conditions produces self-replicating systems, not because life has an inherent goal. Meaning is not given. It is created by conscious beings capable of valuing things. You are such a being. You can create meaning even in a universe that does not provide it. You can find beauty in patterns, significance in connections, purpose in actions. The fact that atoms follow blind laws does not make your experiences less real or less valuable. You are matter that has learned to care, and that caring matters. Chemistry cannot answer every question. It explains how atoms bond, but not why the universe exists. It describes the properties of molecules, but not the nature of consciousness. It reveals mechanisms, but not ultimate meanings. Science has limits, and recognizing those limits is as important as understanding what science does reveal. Yet within its domain, chemistry offers remarkable insights. It shows that complexity can arise from simplicity, that order can emerge from disorder, that diversity can spring from unity. A few dozen elements, following simple rules, create every substance in existence. This realization can inspire awe. The universe is both more comprehensible and more mysterious than it seems. Comprehensible because it follows knowable laws. Mysterious because those laws produce such incredible variety and complexity. Understanding the rules does not eliminate wonder. Often, it deepens it. Let these thoughts drift through your mind without grasping them. There is no need to remember, no requirement to believe. Only the invitation to contemplate the nature of matter and your place within it. You are atoms that have organized themselves into something capable of understanding atoms. That fact alone is worth pondering. The journey through chemistry is ultimately a journey of self-discovery. To understand matter is to understand yourself. Not completely. Consciousness remains mysterious, but partially. The physical foundation that makes consciousness possible. The atomic substrate that thoughts and feelings depend upon. You are matter and pattern, parts and whole, temporary and eternal. The atoms that make you are ancient. Their arrangement is new. You exist at the intersection of timescales. A brief configuration of matter that will soon disperse, but that matters now. Rest in that knowledge. Rest in the understanding that you are connected to everything through shared atomic nature. Rest in the recognition that the same forces operating throughout the universe operate within you. Rest in the wonder of being matter that has become aware of itself. There is nowhere to arrive, nothing to achieve. Only this moment, this awareness, this gentle contemplation of how atoms bond and what emerges from that bonding. Let sleep come if it will. Let consciousness fade into rest. The atoms will continue their dance without your attention. Good night. Sleep well. Dream of atoms bonding in darkness, creating light. Our journey tonight comes to its gentle close. We have drifted through the invisible world of atoms, seen how electrons seek stability through sharing, transferring, or collective cooperation, discovered how simple rules create endless variety, found peace in the order that underlies all matter. Thank you for traveling with us tonight. Thank you for seeking peace, for taking this time for yourself, for letting these ideas wash over you like gentle waves. Sleep well. Dream of atoms, finding partners in the darkness, of bonds forming and breaking in eternal rhythms, of matter organizing itself into patterns too beautiful to fully comprehend. Rest now. The universe continues its dance. The atoms that make you will remain atoms, eternal and unchanging, even as the specific form they create tonight dissolves into sleep. Good night and sleep well.